The ball of mass m starts at a distance h naught above the ground. Its weight mg acts downwards upon it, giving it a downwards acceleration of g. When it hits the floor, it has a downwards velocity v, because the collision is entirely elastic and the floor does not move. After the collision, it has an upwards velocity of the same size v. After a time t, it has returned to the same height above the ground because no energy has been lost. We can split this motion up into three sections. Over a time t1, the ball falls from a height h0 to hit the ground, and we can work out the speed at the bottom using the Suvat equations of motion. Over a time t2, it then elastically rebounds from the ground. There's another time t3 over which it returns to height h0, and by symmetry, we know that this time is exactly the time that it took to fall in the first place, t1. We should now look in more detail at what happens over the time period lasting for time t2. The weight of the ball still acts downwards upon it, and now there is a force due to the floor acting on the ball upwards, which I label here as F. For the rest of this question, I will take downwards as positive, as the final force I'm looking for, the ball on the table, will act in the downwards direction. We can calculate the impulse of these forces on the ball. The total force is mg minus F, and is integrated with respect to time, from the time t1 to a time t1 plus t2. And that's equal to the change in momentum of the ball. Since the ball changes in momentum from going downwards to travelling upwards, the change in momentum is minus 2mv, because I've defined downwards to be positive. During periods t1 and t3, the ground exerts no force on the ball. We can then use this to work out the average force that the ball exerts downwards on the table. This is given as esh dash bar. We know that this force is equal and opposite to the force of the table on the ball. So the time average of this force is equal to minus 1 over t multiplied by the integral of f with respect to time for one complete bounce from time t equals 0 to time t equals capital T. As f equals 0 for the time when the ball is not in contact with the table, we know that the integration is actually equal to the integration from time t1 to time t1 plus t2, the time period over which the collision of the ball with the floor takes place. You can now substitute in the value that we've got for this integral and solve the problem.